Okay, so picture this. You're scrolling through social media, right? And you come across some health post,
Hmm.
and it's full of like super technical terms,
Yeah.
like straight out of a medical textbook or
Well,
something.
sure. Like,
It can be tough to decipher all that online medical jargon.
totally. It's like trying to follow a conversation you're invited to.
Exactly. And that's something we all run into.
Definitely. And, with so much health information being shared online, especially on social media,
Right.
the language people use to talk about medical stuff gets really diverse.
Uh-huh.
It often veers way off from the standard medical terminology.
Makes sense.
And this is where biomedical terminology normalization comes in.
So biomedical terminology, normalization.
Yeah.
What's the big idea here?
Basically, it's like translation.
Right.
We're taking all those different non-standard ways people refer to medical concepts.
Right.
Could be slang abbreviations, lay descriptions you see in forums.
I see.
And we're systematically mapping them to a single agreed upon term
Okay.
in a standardized medical
Got
database
it.
like LS, MEDRA, ICD, SLOMP CT.
Right. Those are the big ones.
Yeah, those are like the authoritative dictionaries of medical language.
Okay, so someone uses a casual term online.
Right.
And this system aims to find its equivalent in that standardized language.
Exactly, like finding the medical version of the word.
That's helpful. And UMLS, that's like one of those Rosetta Stones we talked about before.
Exactly. It's all about creating a common understanding.
Yeah, in a space where the language can be all over the place.
Absolutely now. But why is this standardization so important?
Good question. What practical problems does it solve?
Well, it's crucial for several key applications.
Okay.
Take data analysis, for example.
Okay.
If researchers are studying, say, the prevalence of a symptom mentioned online,
Uh-huh.
they need a way to group all the different user descriptions under one unified term.
I see.
Without normalization, it's like trying to count apples.
Yeah,
When some calling them breadfruit and others crisp spears.
right. That analogy makes sense.
And then it's super important for clinical decision support systems.
Okay.
Making sure the information presented to healthcare professionals is consistent and clear.
Got it.
No matter how a patient might initially describe their issue.
Right. Consistency is key in medicine.
Absolutely. And looking ahead to medical dialogue systems.
Those AI-powered ones.
Exactly. Those will need accurate terminology normalization.
So they can understand what patients are saying.
Yeah, and give appropriate responses.
Okay, so how have researchers traditionally tackled this challenge?
Well, the main approach has been the recall and re-rank framework.
Recall and re-rank?
Yep, first you recall a set of potential standardized terms
Okay,
that might match the non-standard input,
got it.
and then you re-rank those candidates to find the best match.
Makes sense. And within that framework, what's been the go-to technique?
For a while, it's been the pre-train fine-tuning paradigm.
Pre-training fine-tuning sounds like a lot of work.
It can be.
Can you break that down a bit?
Sure, so you start with a large language model like BERT,
Okay.
trained on tons of general text data.
So it has a broad understanding of language.
Exactly. Then you fine-tune it
Ah.
by training it further on specific data sets
Okay.
with non-standard medical mentions and their corresponding standardized terms.
So you're teaching it the specifics of medical language.
Exactly. How to link different ways of expressing the same concept.
And this new research we're diving into today points out some limitations with this pre-training fine-tuning.
Yeah, there are some definite drawbacks.
What are the big ones that led to this new research?
Well, one major issue is the cost of retraining.
Okay.
Medical knowledge and terminology, they're always evolving.
Right, always new discoveries.
Exactly. So term bases like UMLS are regularly updated.
Makes sense.
But if those term bases change or the way we link terms is revised,
Mm-hmm.
you often have to retrain the whole model
Mm-hmm.
or at least update it significantly.
And that's time-consuming and expensive.
It can be very, and another challenge, especially with social media,
Yeah.
is the shortness of both the user mentions and often the standardized terms themselves.
Right, they can be very brief,
Exactly. And short text lacks context,
which can lead to ambiguity.
especially in the complex world of medical terms.
Like a tweet saying stomach bug could mean a lot of things.
Exactly. It could be gastroenteritis, food poisoning, even symptoms of something else.
Right, so disambiguating those short mentions is a big hurdle.
For sure.
So given these limitations, what's the new approach this research is taking?
Well, they're exploring a tuning-free approach.
Tuning free?
Yep, using large language models or LLMs.
Okay,
The idea is to tap into the vast knowledge and reasoning skills.
that these LLMs already have.
Exactly, from their initial training on massive data sets.
So no need for further fine-tuning.
That's the key, a big shift from the traditional methods.
So this deep dive is all about understanding this new LLM-based framework.
Right, we're going to unpack the key innovations and components.
Sounds good. What's the first piece of this puzzle?
Let's start with that challenge of short texts.
Okay, the lack of context.
Exactly. Their solution is something they call knowledge cards.
Knowledge cards. Interesting. What are those?
Basically, they're like dynamic expansions of those short texts.
Okay.
Created by an LLM,
Ah,
they provide valuable context,
got it.
like descriptions, explanations, intended meanings.
So they add back the missing
Exactly.
So how are these knowledge cards made?
This is where their terminology expert agent comes in.
Okay.
It's an LLM instructed to act as a medical terminology expert.
I,
And to generate the knowledge cards, it
mhm.
uses something called retrieval augmented generation, or RAG.
Reg, we've heard that before.
Yeah, it enhances the LLM's knowledge.
By letting it consult external sources
Right, in real time.
to generate more accurate.
Precisely in this case,
Yeah.
the terminology expert agent uses both general search engines.
Okay.
They mention DuckDuckGo specifically and specialized medical knowledge bases,
Like ULS?
like the ULS 2023A version.
Okay, so it's doing its research.
You got it. It's pulling in info from trusted sources.
They build a more complete understanding.
Exactly. And the researchers even provide the specific prompt
Oh, cool.
that guides the LLM in this knowledge card generation process.
So the prompt tells the LLM to be a terminology expert.
Yeah. And to create a clear, concise knowledge card
Okay.
covering the terms, type a summary and explanation, and the intended meaning.
All based on the references and its own knowledge.
Exactly.
So we have these richer knowledge cards now. How are they used in the normalization process?
So now we get to embedding-based retrieval.
Embedding-based retrieval.
Yeah, the idea is to create a numerical representation
Okay.
called an embedding or a vector
Got it.
that captures the meaning of both the short term and its knowledge card.
Makes sense.
They use a powerful embedding model for this text embedding 3 large from OpenAI.
Okay.
It's like turning words into a code where similar meanings have similar codes.
I see.
So they have these embeddings for both the term and its knowledge card.
Right.
And then they combine them to create a knowledge-enhanced representation.
Knowledge-enhanced representation. Okay.
This combined vector holds way more information
Than just the embedding of the short term alone.
Right, because it includes the context from the knowledge card.
And how does this help find the right standardized term?
So they use something called cosine similarity
Okay.
to compare the knowledge-enhanced embedding with the embeddings of all the standard terms in their database.
So, okay.
Cosine similarity measures how semantically related two vectors are.
So terms with a high score are likely to be similar in meaning.
Exactly. Algorithm 1 in the paper details this whole process.
So it's comparing those codes, seeing how close to are.
Yeah, the closer the code, the closer the meaning.
Did this approach work well in their tests?
Oh, yeah. Their results in Table 1 are really promising.
Okay.
They looked at the hit rate,
Uh-huh.
which is how often they find the right standardized term.
In the top results.
Exactly. And across several data sets.
Okay.
Ask Patient, TIDRL, and SMN4H17.
Right.
Using knowledge cards significantly boosted the hit rates.
Compared to using just the term name.
Exactly. And figure A4 shows how RAG improves the quality of those knowledge cards.
So that's a big win for the knowledge enhancement step.
For sure.
So the knowledge cards help narrow down the possibility.
Yep. Now what's next?
What's the next innovation?
Now we come to the Innovative Multi-Agent Collaboration Ranking Framework.
Innovative multi-agent collaboration ranking framework. Wow, that's a mouthful.
It is, but it's a really cool concept.
Okay, tell me more.
They use multiple LLM agents working together.
Multiple agents?
Yep, each with a specific role.
Interesting. So it's not just one LLM making the decisions.
No, it's a team effort.
I like it. So who are these agents?
Well, besides the terminology expert agent we talked about, they have a clinical doctor agent,
Okay.
an outpatient doctor agent,
Yeah.
internet doctor agent.
Interesting. What do they each bring to the table?
Each agent has a specific system prompt
Okay.
that defines their persona, their expertise, and their viewpoint.
Got it. They're all looking at the candidates from different angles?
Exactly. Like the clinical doctor might focus on diagnosis.
Right. Considering potential diseases.
Exactly. The outpatient doctor might focus on common medical issues.
And the internet doctor.
But think about how people search for health info online.
That's really clever, bringing in those diverse perspectives.
It is. And then there's the top K ranking module.
Top K ranking.
Described in Algorithm 3,
Okay.
the terminology expert agent takes the initial list of candidates and narrows it down to a smaller number.
Makes sense. How many?
They used K equals 10 in their experiments.
Okay, 10 candidates.
Yeah, and they use a divide and conquer approach.
Okay.
Breaking the list into smaller groups for ranking.
Got it. And figure A2 shows the prompts they use for this.
Right.
So the terminology expert does some initial filtering.
Exactly. Creates a short list of the best candidates.
Then what happens?
Then it's time for the multi-persona re-ranking module.
Multi-persona re-ranking.
Also in Algorithm 3,
Okay.
the top 10 candidates go to the 3 medical persona agents.
The clinical, outpatient, and internet doctors.
Yep, and each one re-ranks the candidates from their perspective.
Using specific prompts.
Right, you can see them in figure A3.
So each agent gives their expert opinion on the best match.
Exactly. And to help them even more, they
Mm.
use some cool prompt engineering techniques.
Oh, like what?
One is chain of thought or COT instructions.
Okay, what's that?
It encourages the LLMs to explain their reasoning step by step.
Ah, so they have to show their work.
Exactly. It helps make the outputs more accurate and reliable.
Makes sense. So what else?
They also use demonstration selection, or they use those knowledge-enhanced embeddings
Mm-hmm.
with a nearest neighbors algorithm.
Uh-huh.
They used K equals 10 neighbors.
Okay.
This gives the LLM agents relevant examples
Got it.
of past non-standard mentions and their correct mappings.
So it's like showing them how similar cases were handled.
Exactly. Algorithm 2 explains this process.
Okay, so that gives the agents more context.
Yeah, they also use a balanced candidate grouping strategy
Okay.
and added those demonstration examples to each group.
So they have even more information to work with.
Yeah.
So now we have all these rankings from the different agents. How do they combine them?
They use an ensemble learning approach
Ensemble
as
learning.
a way to aggregate the rankings,
Okay.
mainly through a voting system.
Oh.
Prioritizes both the average rank
Uh-huh.
and how often a term is ranked first.
Makes sense.
And if there's a tie, the terminology expert's ranking breaks it.
So it's a democratic process with the expert as the tiebreaker.
That's a good way to put it.
And how did this multi-agent system perform in their tests?
Really well. Their results in Table 2 are impressive.
Okay.
Their tuning-free approach was competitive with both unsupervised and supervised methods.
Wow, even with methods that involve fine-tuning.
Exactly, and all that without the need for expensive routing.
That's a huge advantage.
Definitely. And they also did experiments to see how each component contributed.
Right, the ablation studies?
Exactly. Table 3 shows the results of those experiments.
On the SMM4H17 dataset.
Yep, they removed each component one by one
Okay.
and saw how it affected the performance.
Looking at HR10 and accuracy.
Right, and the results show that each component makes a real difference.
They all contribute positively.
Absolutely. They also validated the multi-persona ranking across all datasets.
Okay,
You can see that in Appendix Table 5.
got it.
And they even looked at using different LLMs for the agents.
Interesting.
Yeah, Table C shows how performance varied with models like GPT 3.5-Turbo 1106.
So they really did a thorough job testing their system.
They did.
So what are the key takeaways from all of this?
Well, the biggest one is that they created this innovative tuning-free framework.
Right, using LLMs for terminology normalization.
Exactly. And knowledge cards are a key part of that.
By adding context to those short terms.
For sure. And the multi-agent collaboration is a big innovation.
With all those different perspectives.
Yep. It shows real potential for accuracy without fine-tuning.
Which is a big step forward from traditional methods.
Absolutely. And to encourage more research,
Yeah.
they've made their code and data public on GitHub.
That's great for the field.
It is under Johnny Fan's rank norm.
I'll have to check that out.
You should. And of course, every research project has its limitations.
Right, what did they identify?
Well, they noted that the knowledge cards. Yeah.
While helpful can sometimes lack precision and structure,
Okay.
they also ran into some formatting inconsistencies.
With the LLM outputs.
Yep, and the randomness of some LLMs is a factor too, even with careful prompting,
Right. And then there's the computational cost of using LLMs.
especially with multiple agents.
Exactly. And they pointed out that their evaluation focused on social media.
So more research is needed on clinical data sets.
That's right.
And what about future directions? What are the big open questions?
Well, they're wondering how to make knowledge cards more precise and structured.
Okay.
And how to better handle those formatting issues.
Mhm.
And how to reduce the randomness of LLMs.
Makes sense.
And can we make the framework more computationally efficient?
Real world use.
Exactly. And how would it perform on clinical data sets?
Right.
And could multi-round interactions with the LLMs improve things even more?
Lots of exciting avenues to explore.
Definitely.
So for our listeners, what are the most important insights to take away from this deep dive?
Well, the main takeaway is this new tuning-free multi-agent framework.
Right, using LLMs to standardize medical language online.
Exactly. And knowledge cards are crucial for adding context.
And the multi-agent ranking process
Yep, with those different perspectives.
shows great promise for accuracy without fine-tuning.
Definitely. It's a real advance over traditional methods.
This has been a fascinating look at a cutting-edge approach.
It has.
And as LLMs continue to develop,
Mm.
I'm really curious to see how frameworks like this will change things.
Me too, how they'll impact how we understand and process all this medical information.
Exactly, and what applications will emerge.
It's a field full of potential.
It is, and maybe our listeners will be inspired to check out the code and data.
I hope so.
Thanks for this deep dive.
My pleasure.